Welcome everybody. In this session I would like to talk about studies in amorphous material characterization using pairwise distribution function analysis. Before I get started, I'd like to thank my colleagues Meredith Xu and Joe Ferrara for their support and insistence in this endeavor. So why perform structural analysis of amorphous materials, and why use atomic pair distribution functions, or PDF, to perform this analysis? It turns out that an increasing number of pharmaceutical actives are non-crystalline in nature, and appropriate characterization techniques have to be developed to keep up with this industry trend. The ability to characterize both molecular structure and local packing for non-crystalline materials is of significant importance for pharmaceutical companies. Structural analysis of PDF traces clearly reveal both molecular and material structural fingerprints within the total diffraction signal. To give you some examples where this might be useful or important, for example, if a newly synthesized active remains non-crystalline, then PDF offers a methodology to verify molecular structure in the solid state. This is one of only very few methodologies that are available to elucidate molecular structure itself inside the solid state for materials that are non-crystalline or amorphous. The use of kinetic manufacturing techniques can induce some molecular degradation during production of the non-crystalline forms. Utilizing total diffraction and PDF analysis can help identify this degradation in the early stages before it becomes an issue downstream. Due to the metastable nature of non-crystalline materials, you'll find that different production pathways will influence the local molecular packing, which we call the material's fingerprint. This material's fingerprint can be extracted from PDF analysis and can really help you guide your production process and ensure that you're consistently making the same disordered material each time. As a last point, which is important for IP and for those of us who do molecular modeling for polymorph identification, local molecular packing and molecular conformation inside the non-crystalline materials can be related to parent crystalline forms. Now, the developed PDF analysis approach I'm going to talk about today uses two orthogonal analysis methods. The first of these is by total diffraction, and the second of those is histogram RDF methods. The combination of the two together appear to be robust enough to address these long-standing analytical challenges. So how does this orthogonal modeling approach actually work? Well, both of the approaches, just put on a laser pointer here, both of the approaches are based upon an atomic level model of the molecular entity itself. The Debye total diffraction modeling approach takes that molecular model and we can directly calculate the expected total diffraction profile, which is shown over here on the left-hand side. The total diffraction profile can be readily converted to the QS of Q minus 1. This is the representation of the measured data that you would derive before going into the Fourier transform to determine a PDF. So from the Debye total diffraction approach, we can directly go from an atomic level molecular model to simulated measured data to an expected QS of Q minus 1. This is all direct calculation without doing any Fourier transformation at all. The alternate approach is to go through the histogram RDF calculation. This will again take an atomic level molecular model, directly calculate the radial distribution function, and from that you can readily derive the pairwise distribution function over here on the right-hand side. So this calculation pathway, again, is a direct pathway requiring no Fourier transformation at all. So when we combine these two orthogonal approaches, we have direct data determined on both sides of the Fourier transform by transforming backwards and forwards between the two, we can compare them and see how well each of these approaches compare with each other. Each approach has its own approximations that go into it. Fortunately, these approximations are orthogonal. So it really is a very robust approach to evaluate your modeling process to give you a pairwise distribution function. To illustrate how the histogram methodology actually works, I've given you this example here for indomethacin. On the top left-hand side, we have the molecular model of indomethacin. This is taken directly from the Cambridge database. And the RDF is directly derived by a summation over all the atom-atom distances, or the atom pair distances, within the histogram itself. And on the plot on the right-hand side here, this blue line is simply the radial distribution function derived by summing over all the atom-atom distances in this molecular model itself. Now, the PDF is simply calculated by subtracting the mean or the effective mean number density from the radial distribution function. Now, for bulk material, the mean number density in molar units in this case follows this gray solid line going up here. But as we're only dealing with a single molecular entity, we have to derive what's called an effective mean number density, which is limited by the size of the molecule itself. And this is the determined, or the effective mean number density for indomethacin. Once you've subtracted the mean number density from the RDF, you simply divide through by the distance, and that gives you directly the pairwise distribution function. The real power of the histogram approach is its flexibility in dealing with molecular modeling, as shown in this example here. You can readily change occupation number for each of these atoms, the thermal vibration, the uncertainty, bond distances, and molecular conformation. These can be readily changed and the RDF recomputed on the fly. This gives you the ability to dynamically change your PDF calculation and then fit that to measured data. This final slide on the histogram approach just brings it all together, starting with our molecular model. Over here on the top left-hand side, we determine the radial distribution function by summing up a histogram of atom-atom distances, determine the effective mean number density, and then we can directly calculate the pairwise distribution function itself. So these are all direct calculations that do not require any Fourier transform approach at all. Now we will consider the Debye total diffraction approach to the modeling. Now, as its name suggests, this is a total diffraction approach, and this means that any feature within your atomic level model will give a fingerprint in the diffraction data itself. As an example of that, consider this very small molecular entity here, acetyl chloride. When we pass that through a Debye calculation, we see a dominating response at lower diffraction angles. This is the small angle scattering from the envelope of the molecular entity itself. Now, we can use that small angle scattering response to model molecular envelopes. In fact, we do that routinely in protein structure solution, and you'll see some other presentations in this event that will talk about small angle X-ray scattering and molecular envelopes. But in the particular exercise we're doing here today, looking at pairwise distribution function to model small and medium-sized molecular structures, then typically the small angle scattering is not very useful for us. What we really want to focus on is the wide angle scattering that has all of the interatomic distances encoded within it. Fortunately, we have a Menke correction, or the Debye-Menke approach, which we can apply to the Debye total scattering response, and that effectively removes or corrects for the small angle scattering. Now, it's not exact, it is approximate, and for highly asymmetric molecules like long chains, it's sort of problematic. But for molecules that are more three-dimensional in nature, then this correction is pretty exact. So, as I said, for total diffraction, features of the molecular model, the atomic level model, they give their own fingerprint within the measured data. And one of those challenges is small angle scattering from small molecule sizes. The total diffraction response methodology has some other limitations as well, because it's very difficult to model randomness. So if you want to model thermal vibration in a molecule, or the effect of functional group rotation and various randomness, the only way to really do that effectively is to do the simulation multiple times with many thousands of molecules with all slightly different atomic parameters, different functional group positions. So that presents usually quite a large computational overhead. It's not so flexible as the histogram approach in terms of changing molecular models to fit measured data. This slide illustrates how the Debye total diffraction approach is utilized to give you the Q S of Q minus 1. That's the other data set on the other side of the Fourier transform to the pairwise distribution function. So we again start off with our molecular model over here on the left-hand side of indomethacin, and then we pass it through our Debye calculation module. This will give you the straight Debye response here in orange. We can then do the Debye-Menke correction to partially correct for the small angle scattering from the shape envelope of the molecular entity. So in blue is the Debye-Menke response. It only impacts the Sachs region. The wide angle scattering region is unaffected by this correction. It will also give us the independent coherent cross-section here in gray, and you'll notice that the Debye response is asymptotic to the independent coherent response out at high 2 theta values. And we'll also get the coherent scattering cross-section as well. Now, QS of Q minus 1 is easily determined from these calculations by taking either the Debye or the Debye-Menke response, subtracting the independent coherent cross-section, and then dividing through by the coherent cross-section. This will give you QS of Q minus 1 in molar units. To go from our QS of Q minus 1 to a pairwise distribution function, we have to pass through a Fourier transform. In order to do the Fourier transform, we have to ensure that the QS of Q minus 1 has the appropriate form in order to go through the Fourier transform without generating too many ripples or artifacts. To do that, we'll have to damp our QS of Q minus 1. So here in orange is the damped QS of Q minus 1 derived by putting in a windowing function prior to the Fourier transform itself. Then to calculate the pairwise distribution function, we just pass that through a Fourier sine transform. So how well do these two orthogonal approaches agree with each other? Are they going to give us the same PDF or not? And that's what I illustrated in this slide. For indomethacin, the gray PDF over here, this is calculated using the Debye model through measured data or simulated data to QS of Q minus 1, and then through the Fourier transform. And the red is the histogram approach from a list of atomic d-spacings. And overall, the agreement between these two orthogonal approaches is really, really very good. As I've mentioned, both approaches have their own approximations that go into them, but they do tend to be orthogonal in nature. They balance each other out. So when you combine them together, you get something that's pretty robust. And certainly for these simple molecular examples here, the agreement between these two orthogonal approaches is really, really very good. And just to show you that the last result wasn't just an accident or a fluke, here is a similar approach done for nifedipine, again a molecular model taken from the Cambridge Structural Database. And here we have the result of the two orthogonal approaches. The gray is the Debye model, and the red is the histogram model. I think you'll agree that overall the agreement is pretty spectacular. So let's see how we would combine together these two orthogonal analysis methods to generate PDFs on a broad range of experimental data. And the data I'm showing here were collected on glassy indomethacin on a wide variety of different X-ray diffraction platforms. In the top, we have data collected on a Miniflex 600 system. This has an automatic divergence slit, only runs at 600 watts using copper in reflection mode. This is a theta 2 theta configuration. The next one down is collected on the Smart Lab. This is using copper radiation, reflection measurements on a milk quench sample in a silicon sample holder. The next two are both collected with molybdenum radiation, hence the longer range shown in Q here. The first one is with the Smart Lab SE. That's measured in transmission using a capillary. The sample was milk quenched directly in the capillary in this case. And the last one is the synergy measurement. For this measurement, we took a single grain of material and mounted it in transmission, did like a micro diffraction single crystal type measurement. And I will say that the sample for the Miniflex, that was milk quenched and then crushed to give a powder before the sample was made. And for the Smart Lab copper reflection, that was milk quenched directly into a low background silicon reflection holder. And I think you'll agree that once we go through the data processing, that all of this data, within the limits of the X-ray wavelength used, looks essentially the same. And that's one of the things we're trying to enable with a PDF platform, is that it doesn't matter which of the instruments you use, you'll be able to generate instrument-free data to calculate the PDF from. So if we take that measured data and we then convert that to QS of Q minus 1, we get the trace in blue here. Again, this is very, very typical for total diffraction responses. We start to pick up the higher noise at higher Q due to the way that QS of Q minus 1 is actually calculated. And we can compare that with what we'd derived previously. This is our Debye-Menke model, which we can also directly calculate QS of Q minus 1. All of this can be done before we hit any Fourier transform. And we can see two sort of remarkable things about these two data sets when we compare them together, the measured against the model or simulated data. At higher Q, let's say above about 6, let's say, inverse angstroms, then the Debye-Menke QS of Q minus 1 agrees fairly well with what we're actually observing in the measured data itself. And we sort of label this one the molecular fingerprint region. So the QS of Q minus 1 derived directly from the Debye approach for a single molecule follows this high Q diffraction response really, really quite well, very well indeed, in fact. It's a bit misleading to call it a molecular fingerprint region because the molecular fingerprint exists over all of this diffraction region here. It's just that it's more clearly visible in the high Q region. Now in low Q, below Q of 6 or 5 maybe, now we see there's a substantial difference between what we calculate with our total diffraction model for a single molecule and actually what we observe in the measured data itself. And this is due to local packing of the molecules because we don't have that in our molecular model. All we have in the model is just a single molecule. Nothing about packing or solid state, nothing at all. This is just like a dispersed molecule in nothing. So this difference here, we call this the materials fingerprint region. And this depends intimately on how the molecule is packing within the solid or the liquid state. Now we can do the same comparison directly in the measured data, although this has been converted to electron units here. So we've removed absorption, Lorentz polarization, and the like. The measured data is in gray, and the Debye-Menke response here is in green. And again, the asymptote in orange is the independent coherent cross-section. And just for completeness, I've included the Compton scattering in this one. And as we've seen up here with QS of Q minus 1, at high Q, the simulated data for a single molecule closely follows the measured data. And we see the same here. For diffraction angles beyond about 35 degrees 2 theta, again, this is with molybdenum, the Debye response for a single molecule closely follows the measured data itself. And this is extremely important, as it gives us a very powerful way to normalize our data prior to doing QS of Q minus 1 and prior to doing Fourier transformation. At low angles, we see the same as we saw in the QS of Q minus 1. The measured data is nothing like the simulated Debye-Menke data. And again, it's because our molecular model doesn't have anything in it at all that teaches us about molecular packing. This is all in the measured data itself. This slide essentially summarizes my narrative from the previous slide, but what I really wanted to emphasize here is that for this local packing, the material's fingerprint, in the measured data, this is clearly observed in the lower 2 theta or the small q or lower q diffraction range. Now, this actually gives us an interesting opportunity. So in principle, if you know your molecular structure, then you only need to measure in the low q range in order to determine this material's packing fingerprint. And in principle, this could be performed with copper radiation with this appropriate normalization, taking into account that we know what the molecular structure actually is. And this is something I'd like to investigate in the next few slides. To illustrate how this might work, I've used nifedipine as an example here. The data shown in blue on the bottom. This is measured data on glassy nifedipine. This was measured in reflection mode using a silicon low background holder using copper radiation. And we only measured out to 80 degrees. So normally this would be considered to be a very much truncated range to do pairwise distribution function type of analysis. In orange here we have the Debye or Debye-Menke response as calculated. And we know that if the molecular structure is fixed, or we take as given we know what the molecular structure is, then at high 2 theta, the measured data must follow this Debye-Menke calculated response itself. And so this gives us a very powerful tool for normalizing measured data on smaller ranges to give it the appropriate normalization. Typically, if we were normalizing for pairwise distribution function analysis, we would use the independent coherent cross-section, so in gray here. But you can see that on this limited range out to 80 degrees with copper, that we do not achieve any asymptotic behavior at all. So it really is hard to appropriately scale the data at that point. However, if we scale it to the Debye-Menke, which is assuming we know what the molecular structure is, then we have a very, very robust scaling approach. Furthermore, we can extend that data on. So if we stop the measured data at 70, we could in principle replace it with calculated data out to whatever 2 theta we wish to extend it to. And that gives us a very, very robust approach to calculate the PDF. Again, this assumes that the molecular structure is known. So we're really not interested in the molecular structure in this particular type of modeling. What we really want to know is how is it packing in the glassy or the amorphous state. In the previous slide, we've seen how we would use the Debye total scattering approach given a molecular model to allow us to normalize and process the data into a PDF. In this slide, we're going to take the orthogonal approach now, because we're going to take a fixed molecular structure for nifedipine, because this is the same fixed structure we used in the Debye model to extend the data. And then using the histogram approach, we'll directly calculate the PDF associated with that fixed molecular structure. And then we can compare this simulated PDF for the fixed structure with our measured PDF determined using the Debye normalization. So when we compare together the PDFs calculated through these 2 orthogonal approaches, what do we actually see? Well, in this figure, the gray represents the measured PDF. This is from glassy nifedipine, measured using copper radiation, that we've gone through the Debye normalization approach and extension before we calculate the PDF. And then in orange, this is a direct PDF calculated from the histogram methodology with the same fixed nifedipine molecular model. You can see at the smaller distances about 1.5 to 2 angstroms, that they are very, very similar. This represents the carbon-carbon distances within the molecular entity itself. But once we start getting to slightly larger distances, between 4 and 10 angstroms, then we see there's a substantial difference between the measured PDF and the histogram calculated PDF. Now, if we just do a straight difference between these two, we get the figure on the right-hand side. So the blue dots are the actual raw data of the difference between the two PDFs. And in orange here, we've built in a model of local molecular packing. This is a stretch paracrystalline model of molecular packing within the amorphous state. And it really does describe the data remarkably well. So this combined orthogonal approach gives us a very powerful tool for analyzing local structure in amorphous, glassy, non-crystalline materials. Within the histogram model, we can incorporate our molecular model itself, and we can combine that with a function that describes the local molecular packing. And the function that we typically use is this stretch paracrystalline function. By combining these two together, we can directly calculate a simulated PDF, which we can then compare to the PDF derived from the measured data utilizing the Debye normalization and extension approach. And again, this was all done with copper, or data collected with copper radiation, out to just 80 degrees to theta. Now, at this point, if you chose to, you can refine the molecular structure and the local molecular packing together to give a better fit to the pairwise distribution function. That wasn't done in this case. There was no further refinement other than to initially extract out this molecular packing function. As with the indomethacin data which I showed earlier, we collect data on glassy nifedipine using a variety of different instrument platforms. And this plot here shows you some of the analysis that we've performed on that data to give us the local molecular packing for glassy nifedipine. In the first figure over here on the left-hand side, this is analysis done on data collected on the SmartLab SE using molybdenum radiation in transmission through a capillary. The material is melt quenched directly in the capillary itself and then sealed. So in some ways, it's almost an ideal environment for the glassy material. When we go through the modeling approach, the orthogonal modeling approach, and then we extract out the local packing, you can see that the calculated paracrystalline function here is in blue, and then the parameters that define that are written here. So the effective paracrystalline D value is about 4.34 angstroms. The spread, which is the variability in that packing, because you're looking at an isotropic packing, but the molecule is not isotropic, so there's a certain variability in that packing distance, and that's about 0.9 angstroms. And the damp value reflects disordering in the paracrystalline packing, and it's a constant at about 0.11. From this, we can actually calculate the effective density in that local packing region, and we get about 1.28 grams per cc, which is very, very close. I think it's about 1% less than what you get for the crystalline material. In the center plot here, this was data collected on the SmartLab in reflection mode, using copper radiation. In this case, the sample was melt quenched directly into the silicon holder. And we can see that the paracrystalline function extracted at the end visually is remarkably similar. In fact, it's the same D value, although now I notice we have a slightly larger spread, or more uncertainty in the reproducibility of that D value itself. And the final data shown on the right-hand side, this was collected using Miniflex with automatic divergence slit, reflection again, copper radiation. But now the melt quenched glassy material was crushed to render it into a powder. So this was measurements in theta to theta geometry on a powder. And despite the different sample prep approaches, the packing function again is very, very similar. And the mean D value of that paracrystalline packing is unchanged across all of the models. But now the spread is substantially larger. So the uncertainty in this isotropic packing is a lot more spread out, if you like. And you can see that visually if you look at the first feature in this packing function with the SmartLab SE data with molybdenum. It's a much sharper, well-defined profile, which indicates that mean isotropic packing is pretty well defined. But by the time you reach the the crushed data, that has broadened out quite substantially. And this also significantly lowers the effective calculated density. It drops something like 10% in the calculation from the direct melt quench stored in a sealed capillary to the rendered and ground material that we analyze using the MiniFlex. So we've seen in the last couple of slides that we can actually extract a material's fingerprint by looking at only the low Q diffraction region. And in principle, we can do that with copper radiation measured out to only 80 degrees to theta. But to do that, in order to do that, we have to assume a known molecular structure. Now, in many cases, that's not going to be an appropriate assumption. So once you have your first estimate of this local packing arrangement, the next thing you really want to do is then go on and refine the molecular structure. What can you extract more information about the molecular structure itself? But really, to do that, you'd have to move to molybdenum or silver X-ray radiation. That's actually very, very difficult to do with just copper. And you'd need to collect data to go over the full diffraction range out to Q of 17 or 23 or so, whatever is allowed on your system. Now, when we first talked about extracting molecular structure from amorphous materials using a PDF, the question always comes back, how sensitive is that? How reliable are these structures? Because if you look at the high Q region, there's a lot of noise there, even if you can't collect data for quite some considerable time. So to illustrate how sensitive this technique is to molecular conformation, I actually went through the Cambridge database and I extracted out 6 different conformations for indomethacin from published crystal structures. I then took these 6 different conformations through the same histogram modeling process, compared it to the raw data, extracted out the local packing function, and then compared the goodness of fit across these individual crystal structures. And I think the results are really quite surprising. This figure over here on the right-hand side summarizes the various goodness of fit results, taking each of these indomethacin conformations, molecular conformations, and sequentially passing them through the histogram model and then fitting them to the measured PDF. And we can clearly see that there's one molecular conformation that definitely has a much lower goodness of fit, or much better goodness of fit, I must say. And this corresponds to the gamma crystalline polymorph. This has a single molecule in the asymmetric unit, and that molecule for the ambient crystal structure gives really the best fit to the measured PDF. There's a second one that's close to goodness of fit, and this turns out also to be from the gamma crystalline polymorph, but this was at a slightly lower temperature. And on the lower left-hand side here, this is a comparison between the measured data in orange in QS of Q minus 1 with the best fit molecular conformation taken from the gamma crystalline polymorph. So this really illustrates that even with small conformational changes you get in different crystalline polymorphs, that it's sensitive enough to separate those out as being most likely candidates for the conformation within the non-crystalline or amorphous state. To summarize our journey together through the structural analysis of amorphous materials using atomic pair distribution functions, we have found throughout this presentation that the structural analysis of PDF traces, utilizing the orthogonal approaches of total diffraction and histogram peak modeling, allows a robust determination of local molecular packing in non-crystalline materials. This local packing is considered to be the material's fingerprint and can be susceptible to the manufacturing process. depending on how exactly you've made your amorphous or glassy material and how has it been stored, the whole thermal history, that will directly impact this local material's fingerprint that you can extract from total diffraction and PDF analysis. Now, this local structure analysis can be performed with characteristic copper X-ray radiation and even utilizing different instrumental platforms. But you must have appropriate calibration and normalization to be able to use copper X-rays for instrument-free PDF derivation. With the local structure identified, the same combined modeling approach can also be utilized to verify molecular structure in the non-crystalline state. However, to do this type of analysis, you really do need to use shorter X-ray wavelengths. For example, molybdenum or silver, are they perfect for molecular structure characterization? And I found that for almost all organic materials I've looked at, that molybdenum is just fine. Well, thank you all for attending. It's been my pleasure. Until next time, goodbye.